So, oxidation of alcohols. Three types of alcohol: primary, secondary and tertiary. Primary alcohols, you've got a carbon that's bonded to one other carbon. Of course, in methyl alcohol or methanol, that other carbon is actually H, but we'll just count methanol within that as much as we can. Secondary alcohols, the carbon is bonded to two other carbon groups, so I'll make that R and R prime just so we keep it as general as possible. And then in a tertiary alcohol, the carbon is bonded to the OH is bonded to three other carbon groups. So there is a primary alcohol. Its oxidation number of this carbon is -1. Don't worry about the R group. Hydrogen's +1, which puts a -1 on the carbon. Hydrogen +1, which puts another -1 on the carbon, so it's -2 for the carbon. Oxygen's -2, loses one of those balanced out by the hydrogen here, so the carbon has to be a +1 to balance out the -1 left of the oxygen. So -1, -1, +1, the oxidation number of a primary alcohol is -1. Oxidation level of that carbon is 1 because it's bonded to one electronegative atom. When we first oxidize, we make an aldehyde. Now, the use of a little symbol here, all we're doing with this O in square brackets is we're saying we've oxidized it. We've used an oxidizing agent on this primary alcohol. And when we do it, we make an aldehyde. So you see O in square brackets, it just says oxidation. If you see an H in square brackets, it means reduction. And you're not getting specific about which agent is being used. So let's go to the aldehyde, the first thing made when you oxidize a primary alcohol. This aldehyde here, you can see the carbon's still got its R group. We can't mess with the R groups. But now, instead of it having two hydrogens bonded to it, it's only got one hydrogen. And now, instead of single bonded to the oxygen, it's double bonded to the oxygen. So why don't you pause and figure out the oxidation number and the oxidation level of this carbon now. So I hope you're back, because I am. So the carbon bonds to a hydrogen. The hydrogen's +1, so that's a -1 on the carbon. The carbon then bonds totally to these oxygen. Oxygen hasn't got anything else on it. Oxygen's -2, which makes the carbon +2. So +2 -1, the oxidation number of the carbon in an aldehyde is +1. So you can see we've oxidized it because we have increased in oxidation number. We also have, of course, oxidized it not because we've increased the number of oxygens, but because we've decreased the number of hydrogen atoms. Now, oxidation level, well, now the carbon is bonded twice to oxygens, so that gives it an oxidation level of 2. Now, if we continue to oxidize, and we'll talk more about what I mean by continue to oxidize, then an aldehyde gets oxidized to an carboxylic acid. Excuse me saying an carboxylic acid. Couldn't decide if I was going to say an acid or a carboxylic, so I just kind of messed it up. So here is a carboxylic acid studied in the module on carboxylic acid and its derivatives. Let us look at this carbon and assign the various things. So again, pause and assign them for yourself. So we're back. So this carbon bonds to this oxygen completely, oxygen -2, making the carbon +2. And then it also bonds to this oxygen. Now this oxygen would be -2, but it also bonds to a hydrogen, hydrogen +1, takes care of one of the minuses of the oxygen. So this oxygen is -1, gives the carbon another +1. So the carbon is +2 and +1, oxidation number +3. So again, you can see the oxidation number has increased as it has been oxidized. You can also see, using the old definitions, what's happened to it. We've now gone from having one oxygen and one hydrogen to two oxygens and one hydrogen. So the aldehyde to carboxylic acid is an oxidation because we've increased the number of oxygen atoms. Let's look at the oxidation level for this carbon. Well, it bonds to 1, 2, 3 more electronegative atoms, so its oxidation level is 3. So you can see oxidation level increases as we do an oxidation. Oxidation number increases as we do an oxidation. So primary alcohols, start oxidizing them, you make an aldehyde in which you've lost the H from the alcohol group and H from the carbon, thus leaving behind this aldehyde with this C double bond O, a so-called carbonyl group. And then when we oxidize it further, an aldehyde turns into a carboxylic acid in which it essentially gets another oxygen atom. Now let's think about secondary alcohols. Assign the oxidation number and the oxidation level. Well, the oxidation number, you get +1 from the oxygen, -1 from the hydrogen. This is as far as the carbon is concerned. So its oxidation number is 0, and its oxidation level is 1, bonded to one more electronegative atom. When we first oxidize this, we get the same kind of idea as we do from the primary alcohol going to aldehyde. We turn the OH and one of the hydrogens on the carbon into a carbonyl group. But in this case, it's called a ketone. Ketone is where the carbon that's double bonded to the oxygen bonds to two other carbon-containing groups, two other R groups, as opposed to the aldehyde, which is bonded to one R group and a hydrogen. And we'll talk more about aldehydes and ketones in a module on carbonyl compounds. But anyway, back to our ketone here. What's the oxidation number of the carbon? Well, it's bonded to an oxygen twice. The oxygen's -2, so the carbon must be +2 to balance that out. And its oxidation level is, well, the carbon bonds to effectively two electronegative atoms, so its oxidation level is 2. So again, we see an increase in the oxidation number, we see an increase in the oxidation level, and we see a decrease in the number of hydrogens, all of which point to this being an oxidation. Finally, tertiary alcohols. Here's our general formula of tertiary alcohols. Oxidation number is 1 because the only thing bonded to the carbon is a oxygen that's worth -1, so the carbon is +1, and the oxidation level also 1. However, if you look at this tertiary alcohol, there's no other hydrogen for us to lose. If you look primary alcohol turned to aldehyde, we lose the hydrogen from the alcohol group and another hydrogen. Secondary alcohol gets turned into a ketone. We lose the hydrogen from the alcohol group and we lose another hydrogen. Got a hydrogen on the alcohol group, but we don't have another hydrogen. So under normal conditions, tertiary alcohols cannot be oxidized. Now, if you use really strong, strident conditions, well, then you can break the tertiary alcohol apart and you get a kind of weird mixture, combination of all kinds of things. But as far as we're concerned, you can't oxidize tertiary alcohols. When you oxidize a secondary alcohol, you make a ketone. And when you oxidize a primary alcohol, you first make the aldehyde and then the carboxylic acid. 'Tis worth talking about the oxidizing agents that we can use. Now, by and large, when you look at your A-level textbooks and when you look at many basic organic textbooks, they say we're going to use high oxidation state transition metals as oxidizing agents, because if these metals are in a high oxidation state, it means they'd love to lower that state. They want to be reduced, which makes them good oxidizing agents. Again, further details, go to the first couple of movies in the electrochemistry module. Now, the two big high oxidation state transition metals that one encounters are chromium and manganese. Start off with chromium 6. Now, there is a very famous movie, starring Julia Roberts, the title of which has just come back into my head, Erin Brockovich, story of a waitress in a California town where there was a very high incidence of cancer, and she managed to demonstrate that this was because of a local chemical plant, actually I think it was a tanning factory, pumping chromium 6 into the groundwater. Chromium 6 is a very significant nasty carcinogen. But despite that, it's always discussed as being a really good oxidizing agent, because it is, because chromium 6, that's as high as the chromium can get in terms of oxidation numbers. Now, most of the time you encounter chromium 6 in the lab or in your textbook, because probably you aren't going to encounter it in the lab anymore. Cr2O72- is dichromate, usually found as ammonium or potassium dichromate, so K2, Cr2O7. And then Cr042- is just chromate, again 2-, demonstrate to yourself that the chromium in each of these is in chromium 6. Now, when you take a sodium chromate or a potassium dichromate and you put it in acidic conditions, then you make so-called chromic acid, H2CrO4, which is a fantastic oxidizing agent. Now, What you are told at A level differs a little bit from this. What I'm telling you is that if you take chromic acid, so dichromate or chromate under acidic conditions, it is going to oxidize primary alcohols to acids and secondary alcohols to ketones. Okay, if you're told in your book that if you do this at a lower temperature, you will make the primary alcohols go to aldehydes. That's fine for your A levels. Don't believe it otherwise. If you do wish to convert your alcohol, your primary alcohol, to an aldehyde, then you use one of these reagents here, so-called PCC or PDC. Now, the P in each case stands for this, which is the pyridinium cation, and then the DC, dichromate, and the CC is a chlorochromate. You don't have to worry overly about what these stand for, just PCC or PDC. When you put these in anhydrous conditions, so usually done in dichloromethane as the solvent, then you can turn those primary alcohols to aldehydes. Now, another one, I said that one of the other really nice high oxidation state transition metals is in manganese 7, usually found in permanganate, MnO4-. You do this under acidic conditions, and it is a good, strong oxidizing agent. It's going to take the primary alcohols to acids, the secondary alcohols to ketones. If you do it under reflux, then it will just smash everything up you possibly can. It will break carbon-carbon double bonds and just do all kinds of fun things that we'll talk about in a later extension module. So by and large, when you're oxidizing alcohols, at least on paper, go with chromium-6. You can either use the dichromate and chromate under acidic conditions to take things the whole way, or if you want a milder oxidizing agent that's going to stop at aldehydes, you use anhydrous conditions with PCC or PDC.